We're talking about distributions of continuous random variables. Let's start out with the most famous of all continuous probability distributions, the rock star, the normal distribution. It's also often referred to as a Gaussian distribution, named after Carl Friedrich Gauss, a German mathematician with some tremendous sideburns.
Oh yeah!
The normal distribution supposedly describes a lot of real-world phenomena. And regardless, we frequently assume it does because it has some easy-to-use qualities, which we'll see a little later on. Let's talk about a few properties of the normal probability distribution. The first is it has a bell shape. That is, it looks somewhat like the cross-section of a bell. You may often hear references to the bell curve, which describes a phenomenon which is centered about some mean value, with other values extending from it in both directions with decreasing likelihood. The normal distribution is a bell curve. Social scientists often use the term bell curve. Physicists are the ones who use Gaussian. To engineers and statisticians, it's just the normal distribution. It has two parameters that are familiar to us, the mean mu and variance sigma squared. Mean mu tells us where on the horizontal axis the normal distribution is centered, and sigma squared tells us how dispersed or how variable the distribution is. The larger the value of variance, the wider and flatter the distribution. If random variable y follows a normal distribution, we say that y is normally distributed with mean mu and variance sigma squared, or sometimes standard deviation sigma. The third property is that the probability distribution function, or PDF, is symmetric about the mean. The fourth property is that the two tails of the curve extend indefinitely. That is, the normal distribution assumes that very large and very small negative realizations of the random variable are possible, though with very low likelihoods. And finally, the two general properties of distributions of continuous random variables still hold. The probability of an interval between two values must be between 0 and 1, inclusive of 0 and 1, and the sum of all mutually exclusive and collectively exhaustive intervals must be 1. Recall that with a continuous PDF, the area under the curve gives us the probability. So these two general properties translate into 1. The area under the distribution between 2 points must be between 0 and 1, inclusive of 0 and 1, and the total area under the normal distribution must be 1. The normal PDF has a functional form, which is a function of mu and sigma, plus some other good stuff. This is the equation that generates the bell-shaped curve for f of y. The probability of a particular interval between a and b is found by integrating the PDF and evaluating between a and b. That is a nasty integral, and one that we don't want to deal with directly. Similarly, you don't want to calculate the integrals for expected value and the variance, but as luck would have it, the expected value and the variance are just mu and sigma squared, respectively, the two parameters of the normal distribution. Back to finding the probability of the normally distributed random variable y between a and b. We use what is called the standard normal distribution. The standard normal is a special case of the normal distribution where the mean mu is specified as 0 and variance is specified as 1. The common notation for the standard normal random variable is z, and the realizations are little z or z-scores. Capital Z for the standard normal random variable, little z for the realizations. So how does the standard normal distribution help us? Say that we have a continuous random variable y that is normally distributed with mean mu and standard deviation sigma. For example, y could measure the height in inches of college students. And say we want to know what the probability of a college student being between height a and b. To find that probability, we could integrate the PDF and evaluate it between values a and b, but that's gross. What we do is convert the interval a and b to values on the standard normal distribution axis. The way we do that is with a z-score equation. Z is equal to y minus mu all over sigma. We can then find the area under the curve between two z values using a lookup table. So what does normalizing do for us? Oftentimes people use the term normalizing to suggest that a value is altered to account for its magnitude, such that it can be compared to phenomena measured on a different scale. That's what we're doing with the z-score. We're taking the value on the y-axis, we're subtracting off the mean, and we're dividing it by the standard deviation. That is, we're saying how far away is the y value from the mean in standard deviation units. We're taking out the magnitude of random variable y, and we're only talking about the number of standard deviations away. Let's go back to the example where random variable y measures the height of college students. Say the mean height of college students is 5'8" or 68 inches, with a standard deviation of 2.5 inches. How would I convert a realization of my height, say my height of 6'2" or 74 inches, to a value on the z-axis? Take the z-score calculation of realization y minus mu divided by sigma. That is 74 minus 68 divided by 2.5. That z-score is 2.4. My height is 2.4 standard deviations away from the mean height. The value 74 inches lies 2.4 standard deviations from a mean of 68 inches. The numerator is in inches, and the denominator is in inches, so the number of standard deviations is unitless. Recall that the standard normal distribution has mean 0 and standard deviation 1, so value 2.4 on the z-axis lies 2.4 standard deviations, 2.4 times 1, away from the mean, which is 0. The number of standard deviations is a metric that can be applied to any kind of scale. We could be talking about billions of dollars or hundreds of milliseconds. The z-score gives us a common measure of distance. So how do we find a probability of an interval of a normally distributed random variable? Say we want to know the probability that the height of a person is between 5'10" and 6'1", or between 70 and 73 inches. We convert these values on the y-axis to z-scores on the z-axis. The lower bound on the interval would be 70 minus 68 divided by 2.5, or 0.8. And the upper bound on the interval would be 73 minus 68 divided by 2.5, or 2. The probability that y lies between 70 and 73 inches is equivalent to the probability that z lies between 0.8 and 2. Again, the z-score takes away the units of the original normally distributed random variable. We can then look up the probability that z lies between 0.8 and 2 on a standard normal table, or a z-table. Different z-tables don't always have the same appearance, depending on the textbook that they're found in, but they always provide the same information. We're going to use a z-table that provides the probability of the interval between z equals 0 and a value z. The row on the z-table provides the ones and the tenths digit of the z-score, and the column provides the hundredths place of the z-score. The intersection of the row and the column tells us the probability between 0 and that z-score. For example, if we want to know the probability that z lies between 0 and 1.37, we go to the row associated with 1.3 and over to the column associated with 0.07. The intersection of that row and column gives us the probability between 0 and 1.37, which is 0.4147. Another example, say we want to find the probability between 0 and 2.12. We go to the 2.1 row and over to the 0.02 column, and we find that the probability would then be 0.4830. If we want the probability of z between 0.8 and 2, we find the area between 0 and 2, and we subtract from that the area between 0 and 0.8. The area left would be between 0.8 and 2. To find the area between 0 and 2, we go to the 2.0 row of the z-table and to the 0.00 column. The probability is 0.4772. And then for the area between 0 and 0.8, we go to the 0.8 row and over to the 0.00 column, finding a probability of 0.2881. The difference between these two is 0.1891. The probability that z lies between 0.8 and 2 is 0.1891. That suggests that the probability that y lies between 70 and 73 inches is 0.1891. That is, 18.91% of people have a height between 5'10" and 6'1". Note that the standard normal distribution is symmetric about the mean, 0. So the area above z equals 1.37 is the same as the area below z equals negative 1.37. What is the probability that z is greater than 1.37? Remember that the table gives us the area between 0 and the value we're looking up. Also remember that the table is symmetric about 0, so half the probability lies above 0 and half lies below. That means that the area under the curve greater than 0 is 0.5. Likewise with the area less than 0. So if we know that the probability that z lies between 0 and 1 is 0.4147, that must mean that the probability that z is greater than 1.37 is 0.5 minus 0.4147, or 0.0853. This suggests that the probability that z is less than negative 1.37 is also 0.0853. It takes a bit of practice to get the hang of converting a normal distribution to a standard normal, reading the appropriate probability from the z-table, and so on. We'll do a lot more examples on the board when we have a chance to write things out, but you now have the basics of the normal probability distribution.